Welcome back to the 3n+1 conjecture. We started out trying to find a loop somewhere out in space. And then we figured probably there are no loops, so we started to work on proving that there are no loops. And we focused on circuit loops. A circuit loop of length k goes up for x steps and then back down for k minus x steps. For example, we start with some number, then do 3n+1 over 2 on that number, do that 3 times, and then divide in half twice. With that sequence of operations, there's only one number that loops back on itself, m, and we can calculate its value with this formula. We're lucky this formula is so simple. It's got a numerator, which in this case is 27 minus 8, or 19, and a denominator, which in this case is 32 minus 27, or 5. Since 19 over 5 isn't an integer, this isn't a valid loop. Now we want to show that no matter how many yellow or blue blocks we choose, m is never going to be an integer. Now in this case, at least 5 was smaller than 19, so we had a chance. And previously we looked at greatest common factors, where we also concluded that 2 to the k minus 3 to the x has to be smaller than 2 to the k minus x minus 1, which is stricter, and in fact this never seems to be the case. So for example, take 2 to the 10th minus 3 to the 6th, which is 295. Well, that's way better, way bigger than 2 to the 4th minus 1, which is 15. And we can actually prove that. Let's follow the proof in this case. We can treat this as a difference of squares, and we know from 9th grade how to factor a difference of squares. We get two factors. You can see they're both positive integers by inspection, and even the first part of the first factor is big enough to exceed 2 to the k minus x minus 1, and it works in all cases. So we concluded that no integer circuits for 3n+1 when k and x are both even, because if k or x is odd, the proof breaks down, because this product here isn't necessarily bigger than the first factor anymore, which we assumed before. Okay, now for something new. We can extend this proof to whenever k and x have a common factor, not just when k and x are even. So here, for example, 15 and 9 have a common factor of 3. So we can rewrite it as a difference of cubes like this. And a difference of cubes can be factored like this. It's still a sum factor times a difference factor. And now the sum factor has more terms, starting with x squared. And even that x squared term is big enough for our purposes. We can follow the same idea. So for example, here 2 to the 10th, underscored in red, is plenty big enough to exceed 63. And this reasoning works in all the cases. Sometimes we don't even just have a difference of squares or a difference of cubes, so we have something bigger, and we know that any x to the n minus y to the n can be factored like this. Okay, so no integer circuits when k and x have a common factor. That's actually about 39% of all the choices we can make for x and k. All right, nice short episode. Next time we're going to go time traveling back to 1936. See you then.